All right. Hello, everyone. Welcome to Comp 3430 Operating Systems. Normally, you do not see this interface because I normally do this in the morning in the first section, but I accidentally left the receiver on my mic turned off this morning. And so it's just like a video stream. It's a great video stream, but there's no audio. And so I'm recording this in the afternoon section, and I'm streaming it right now. So the background is a little different than it normally is, and the people that I'm looking at are different than they normally are. Yeah, crisis averted, crisis averted. And I was just confirming that I can see audio showing up in that little green bar, that there's something there. I hope that you are all doing okay. The weather this weekend was so much nicer. I managed to get out for a bike ride yesterday, and I went through the park, and Assiniboine Park, and it's kind of feeling good, like seeing lots of people out and about, seeing families having like barbecues and stuff in the park was just really nice to see. Except, you know, for the forecast that I'm looking at for tonight, which is like 20 below with 2 centimeters of snow. Yeah, so that kind of ended that dream of cycling being a more regular thing for me, but you know, it is what it is. I hope that things have calmed down a little bit for all of you. I hope things are a little bit more like less always on all the time for assignments and stuff. Yeah, I hope things are going okay. So what I want to do today is I want to kind of take a look at condition variables for a little bit more time. My goal for today is that I want to spend some time taking a look at a worked example of using condition variables for a thread pool. Last week, we looked at this like super contrived example of condition variables that was of the form, here's a condition variable, these threads stop. And then when we call pthread const signal or pthread const broadcast, they all wake up and then they stop, then they end execution. And while that's good from a mechanical perspective of like, here's how you can call condition variables, how you can call pthread const wait, and how you can call pthread const signal, I want to spend some more time with a more realistic, properly motivated example as opposed to just this mechanical hyper contrived example. We did look at using a thread pool. We looked at some Oracle thread pool code, but there is so much going on in that. There is so much going on in that, and it is basically overkill for what we really want to think about in terms of using condition variables to indicate to workers that there is work for them to do. And so today I want to spend the class working through an example of building something up that's more complicated than just let's block and wait for this thing to happen, and let's actually start using condition variables the way that they're meant to be used. So let's take a look at thread pools. The goal that I've got for today is I've started an implementation of a thread pool, and I want to have us finish implementing this thread pool. So using condition variables to signal to workers that there is work for them available to do. The code that I'm starting from, I've posted up on the thread management Git repository that's linked in today's section on the course webpage. So if you want to follow along with what I'm doing, and I invite you to follow along with what I'm doing, please clone or pull that repository. I'm going to pop over to my terminal here, and we're going to start taking a look at the directory that we're working in. So I've added this new directory that's called 3430 pool. This is the one that we're going to be working from for today's lecture. And within this directory, there's a number of different things. There's 3 files here that I'm not really going to open. I'm not going to open them because they're not really directly related to what it is that we're doing today. There are 3 files here that are named jobq.h, jobq.c, and testq. This is an implementation of a queue. It's an implementation of a queue as a linked list, and the testq is it's an okay test harness. It's not an excellent test harness. It does some very tiny amount of testing, but it doesn't actually do a huge amount of testing. I'm not really going to look at these because there's an enqueue function and a dequeue function, and that's what we really need to care about in terms of using this queue structure that I've got. The file threadmadness.c, this looks almost identical to the same named file in the thr_pool directory, so it's a client of the interface that we're going to implement. We will take a look at this very briefly to get an idea of what's going on in the client side, so the code that's using our thread pool. And then the other two are 3430pool.h and 3430pool.c. The .h is a simplified interface for the thread pool structure that we saw last class. So last class we saw that big Oracle thread pool structure. This is a simplified version of that interface. And then 3430pool.c is going to be where we're actually going to put the code that we're writing for this example. So I want to start by taking a look at both 3430pool.h and also taking a look at threadmadness.c. I want to look at these two things together. The way that the thread madness implementation here interacts with this thread pool structure is that we start by creating an instance of the thread pool. So we're calling that thread pool create function. The difference between what we had in the Oracle version and what we're doing here today is that we're just going to say that we're going to pass the number of threads that should be launched by the pool at start, and that's it. So in the Oracle version of this, there were like 4 or 5 arguments to this function that changed the behavior of how threads got started, how they were kept around, when they were allowed to terminate, and that sort of thing. But I don't really care about any of that stuff. I just want to start up 10 threads and have them waiting for work to show up. And I don't want to have to manage the number of threads at runtime. So our thread madness code here on the right side, on line 26 here says, please create a thread pool that has 10 threads in it. This code is going to launch 10 pthreads in addition to the main thread of execution. And then it will be allowed to proceed with working with the thread pool. Once we've got an instance of that thread pool object, then we're going to start submitting work to this. So this is where we're calling the thread pool queue function. The thread pool queue function looks a lot like pthread create. It looks a lot like pthread create in the sense that we are giving this function a pointer to another function. And that's ultimately saying, this is the work that I want this thread to do. So the work that we're passing to thread pool queue here is a function pointer to this function up at the top, which is this terrible example of a race condition where we have many threads trying to add to the same variable all across many different threads of execution. We're passing to it some function that we want the thread to execute, and then we're passing arguments to this thing. So total jobs here is just, it's a number that we're passing to this as an integer, and that's going to be what we have in the thread pool worker function to be able to actually do the work that we're asking it to do. The last function that we're going to be working with this thread pool is the thread pool wait function. And despite what the comment says, I'm going to change the comment after class. Despite what the comment says, this basically says finish the task that you're currently working and then shut down. If there is more work left to do, it's not going to finish the work. It's finish whatever you're currently working on and then exit. So there might be jobs left over at the end of execution here, but we really just want to say shut everything down, please, so that we can exit out of the program that we've got right now. So in terms of how this client is using our interface, we create an instance of a thread pool, we send a bunch of work to the thread pool to start working on, and then we tell it to shut down. It might be in the middle of lots of stuff, but just shut down. Just shut down now, and we don't want to wait around for it. We could change the way that we're going to implement this to actually wait for stuff to finish, but we're just saying shut everything down, and then we're all done. So I'm going to quit this thread madness code, and what I'm going to do now is open up the implementation of our interface. I've already defined the structure. Yeah. That's a good question. Are more threads always or universally better? Or should we try to pick something that's kind of in connection to what we've got in our system? The second option is usually the better case. So picking something like, I've got 16 cores on this system, so I'm going to pick something that's smaller than 16 cores, so that once a thread gets a processor, it can just keep working on that processor without getting switched off, assuming that no other stuff shows up in the system at that time. But when we're summarizing this, I'm going to give some examples of why you would choose to use a thread pool, and that's one of the reasons why you might want to do that. Rather than launching 100,000 threads and trying to let them all finish all at the same time, you just launch them 10 at a time and always stick to having only 10 ever running at the same time. Yeah, so that's a good question. The structure that I've got here for the thread pool is that we have a lock, we have a mutex. So many different threads of execution are going to be running in here. Many different threads of execution are going to be running in here, and many different threads of execution are going to be pulling from this job queue. So the job queue is going to be where we put work. We don't start running the code that was passed to us when we call this thread, the thread pool queue function. We don't start immediately working on stuff. Instead, we put that work into the queue, and if someone's available to take it, then it gets picked up and operated on. If no one's available to take it, then it just lives in the queue for a little while longer until somebody becomes available to pick it up. Because we're going to have multiple threads of execution working on the same queue, we will be doing enqueue and dequeue in a bunch of different concurrent places. We want to lock this structure. We want to make sure that there isn't concurrent modification to the queue structure itself. And so we're going to put a lock around the entire structure that we've got for the thread pool. The last thing that we've got here are the number of threads that are currently running in the thread pool, and then a flag that says you should start shutting down. So once this flag is set, by default, it's going to be false. Once we set it to true, once we change its value to true, what we're telling all of the working threads is when you're finished the task you're currently working on, even if there is more work to do in the queue, you should stop. You should just exit and end the thread that you're working on right now. The first function that we're going to implement here is this worker thread function. This is the function where we're going to have our threads sitting around and checking to see if there is work to do, and if there's not work to do, we're going to have them suspend themselves using condition variables. Once they've got work to do, once they're signaled that there is work to do, they're going to wake up and they're going to take something off of the queue to do, and then either go back to sleep because there's nothing left to do, or take another job off the queue. The constructor function here, the thread pool create function, I've already filled this in because this is not an interesting part of the code that we're working with today. But we are allocating dynamically the pool that we're working with. We initialize the mutex and the condition variable that we've got. We initialize the queue that we have for jobs. We set our flag to false, and we set the number of threads to be equal to threads. This is how many threads are currently running in the system. Then we launch the threads. In this code, I'm calling calloc or malloc, so I'm dynamically allocating each thread object, and then I kind of just throw it away. I don't actually care to keep track of what threads are actually running because they're telling me how many are running in that n threads value. They're going to modify that as they're going through it, but I have to pass something to pthread create in that first argument. So I'm dynamically allocating something, passing it to pthread create, and then just letting that thread start up, and then I'm ignoring that I have that handle on there for later. I do this threads number of times, and then my thread pool has started, and I've got however many threads concurrently executing right now. The other one that we're going to spend, the other two that we're going to spend some time looking at today are the thread pool queue function and the thread pool wait function. The queue function is going to have the responsibility of enqueuing work to the queue for the pool that we've got, and then signaling to any threads that are waiting that there is now work for them to do. And the thread pool wait function is going to change the flag that we have for waiting to be true, so we're shutting down. And then all the threads are going to have to be woken up to say, oh, you should check the value of this flag and then shut down after that so that you're not spinning around waiting anymore. One of the things that I do want to do with this as we're going through it is I'm going to get to a certain point, and I'm telling you right now, I'm inserting a bug into this on purpose, but for the purpose of doing debugging with this code, I want to take the time to use LLDB. I want to use my debugger to inspect the state of the threads that are currently executing in this process. And I want to do things like look at the value of locks, and I want to see who holds a lock right now. So if you notice the bug as I'm going through this, awesome, first of all, awesome, but keep your mouth shut. Keep your mouth shut so that we can all try to figure out what this is using the debugger at the same time. All right, so the place that I want to start is in this worker thread function. This is the first place that I'm going to start working. And the assumption that I have here is that we're going to be starting to write this code from the perspective of this thread. The job of the thread is to, one, check to see if there is work. So there's something in the queue. If there is work, then do the work. Take the job and do the work. If there is not work, go to sleep, or suspend, or block until someone tells you there is work. That's the first job. The second job is, if you're being told to shut down, then shut down. That's the two jobs that we've got here. Look for work. If there's work, do it. If there's not work, go to sleep. If you wake up and someone has told you to shut down, then shut down. Exit the thread, return from the thread. So I'm going to write some code, and I'm going to start like this. I'm going to say while pool does not equal null. I've got my assertion here. You must pass me a non-null pool, and I'm going to have my conditional statement here in the form of my loop. So this, I just, instead of putting an if statement, I'm just putting this in my condition for the while loop. If the pool is not equal to null, and I haven't immediately been told to shut down. If I've been told to shut down just after I start, I shouldn't even begin to try doing anything. I should just exit immediately. If I'm exiting, the way that I want to signal to the rest of my system that I'm exiting is by reducing the number of threads in that nthreads variable in my structure. So in my structure, I've got this nthreads value. I'm going to do this. I'm going to say, I'm exiting, tell everyone else, pthread mutex lock. I want to lock it because I'm going to decrement this value. If multiple threads are exiting at the same time, I want to make sure that only one is decrementing it at a time. I want to make that decrease an atomic operation. So I'm going to say pthread mutex lock pool mutex. I'm going to say pool nthreads minus minus pthread mutex unlock. Lock that I'm going to do this decrement operation, do the decrement operation, unlock. Make sure that when I do this decrement operation that anybody else also concurrently executing at the same time as me will not cause me to lose the decrement that I've got there. Yeah?
Better or worse than the atomic operation?
Is it better or worse than? Using atomic integers? So I don't have a good answer for that because it could be that the atomic operations that we're doing with that std atomic header are doing the same thing as what we're doing right now. It's possible for that to happen. I'm going to argue that in this case, if you have 10 threads, this code is only going to run 10 times. 10 times of like microseconds is still microseconds. So it's not going to take long to like acquire the lock and then release the lock. Yeah. I will note though that doing atomic would be better for reducing the surface area of getting into a deadlock or buggy state where you're trying to acquire a lock. You don't need to acquire the lock if it's an atomic variable in the first place. That will be kind of handled on your behalf. Okay, so if we're not in the state of immediately shutting down after we've started, so our thread pool has been created, the pool create function is causing 10 or whatever p threads to start up that are each calling this function. If we're not causing us to shut down immediately upon start, then what I want to do is I want to check to see if there's work. I want to check to see if there's something in the queue of work that we've got to decide whether or not I should suspend myself or proceed with doing the work that I'm able to get from that. So we're going to use a condition variable to do that. And what I'm going to say is I need to acquire the lock before I can use the condition variable. So I'm going to say pthread mutex lock. I want to lock the pool's lock. Once I have been able to acquire the lock, now I'm going to start asking questions about the queue. I want to acquire the lock because I want to be able to say queue size of the queue, pool jobs. If it's equal to 0, there are no jobs currently in the system. And I'm not been told to exit. I'm going to zoom in on this. If there are no jobs for me to work on right now, and I have not been told to exit, then I'm going to pthread cond wait. I'm going to wait, and I'm going to pass my mutex to that. So pool mutex. Our order of operations here is we may be able to acquire this lock. So we can start entering this critical section where I want to start to ask questions about the queue structure that I've got. I'm going to ask this question about the queue structure that I've got. How many items are currently in it? And if there are no items in it, and I'm also told that we're supposed to stay running right now, then I want to suspend myself, and I want to release the lock. There's no work for me to do, so I should just go to sleep and let another thread of execution enter this and find out that there's no work for it to do and also go to sleep. And then eventually all of my threads of execution will get stuck here. They will all be blocked, and they'll all be waiting for work to show up in the queue that we've got. If we are able to say that there is work for us to do, then what I want to do is I want to start getting that job from the queue. I want to take something off of the queue. And so I'm going to say this. If I'm able to leave this loop, I've acquired the lock, I've checked to see that there's no jobs, I'm going to suspend myself and release the lock. Someone has now signaled to me, hey, there's work in the queue. If I'm able to acquire the lock, I will wake up and acquire the lock and go to the top of this conditional statement. The conditional statement now holds the lock. We have the lock held when we get to this point because of what's going on with our pthread condition variables. So I'm going to ask this question about queue size, pool jobs. Is it still 0? And if there's work, so we've been told to wake up because there is work, that will be false, and so we will exit the loop. When we exit the loop, we will still hold the lock. We haven't explicitly released it yet, so we still hold this lock. And so I'm going to ask another question about the queue. I'm going to say, is the queue size, pool jobs, greater than 0? is there work for me to do? So you woke me up. Do I actually have work to do, or are you telling me to shut down or something else? If there's work for me to do and you are not telling me to shut down, then what I want to do is I want to get the job off the queue. I want to take that work for myself. So I'm going to say job is equal to DQ, and I want to DQ an item from pool jobs. I can do this safely. I can modify this queue because I hold the lock. Nobody else is modifying this right now. It's just me, just my thread of execution. I get the lock, I go to sleep, I am eventually woken up, but I hold the lock when I wake up. I test to see if the size of the queue has work in it, yes. I test to see if the size of the queue has work in it, yes. I'm able to pull something off of that queue, and I still hold the lock. I have not given up the lock yet. I'm going to take that job off of the queue, and our job structure has two arguments in it, or two properties in the structure. We've got a function, so I've declared function and arg up at the top of this one, but I'm just going to copy them here. So I'm going to say if the function is the job's job func, and the arg is the job arg. So I'm going to copy these two properties. I'm going to take this job off of the queue. Nobody else will get this because I'm the only one that holds the lock right now. And once I've got the job, once I hold the job, I can release the lock. I want to let someone else wake up and get a job off of the queue if there is work for them to do. So I'm going to release the lock. Nobody else is going to get this one that I DQ'd because I have already DQ'd it. I'm going to unlock the lock, and then I'm going to do the job. And the way that I'm going to do this job is I'm going to call the function. I'm going to pass it arg. I hate function pointers because of how crazy it is to declare function pointers, and I love the idea of function pointers because it's this variable that you can call as a function, and I think that's cool. I think that's really cool. I'm going to do the job. I don't need to hold the lock when I'm doing the job because the job is not, in theory, going to modify the queue because the job doesn't know about the queue. This is something that's been passed to me and it has no idea what my internal structure is. So again, our order of operations. Our worker thread starts up. One of them will acquire this lock, test to see if there's any jobs. There are no jobs. I'm going to go to sleep. I will release the lock. The next thread of execution is going to start. It will get the lock, test to see that there's no jobs. It will go to sleep because there's no jobs and release the lock. The next thread will start up. It gets this lock. It tests to see if there's any jobs. There are no jobs. It goes to sleep and it releases the lock. Eventually, somebody signals us and says, hey, there's work for you to do. So a thread wakes up. It gets the lock by waking up. It's able to start executing once it is able to acquire that lock. It tests to see, is there work? Yes, there's work this time. Yes, there's work this time. Modify the queue, unlock the lock to allow other threads to wake up and get work. Do the work yourself. Is that okay for everybody so far? Eventually, our threads will shut down. We'll tell them that we're doing that pool wait, so we're going to shut down, and eventually they will exit this loop and they will decrement the number of threads that they've got right now. So this is our work function. Now we actually have to allow work to be submitted to us. I want to have somebody be allowed to pass me work so that I can tell these threads that are waiting around for work to show up that there is in fact something in the queue for them to do. So I'm going to go down here to my thread pool queue function. And here is where we're going to start trying to add something to the queue and signal to all these waiting threads, hey, there's work for you to do now. I'm going to test to see if the arguments that were passed to me are not null. I don't want you to pass me a null pool, and I also want you to actually pass me work to do. I don't want my thread that's running the function to get a seg fault because it's trying to run a null pointer as a function. If you have passed me something, then I'm going to initialize this job structure that I've got. So I'm going to say job is equal to calloc 1 size of job t. For the record, calloc and malloc, they're both dynamic memory allocation requests. Calloc is saying the first argument is the number that you want, the number of the thing that you want, and the second argument is the number of the size of the thing that you want. Whereas with malloc, we have to multiply those things together. With calloc, we just specify them as 2 separate arguments. If I'm able to create an instance of this job, then I'm going to copy these things that were passed to me into this structure. So I'm going to say job func is equal to func, and job arg is equal to arg. So these are the values that were passed into me. Once I have this job created, I want to enqueue it. I want to put it into the queue of work for this thread pool. So I'm going to have to block the lock. I do not want any thread of execution to make changes to it, to the queue, while I am making changes to the queue. So I'm going to say pthread mutex lock. I'm going to pass to this pool mutex. I want to enqueue the job. So make sure nobody else is modifying it. Make sure nobody else is modifying the queue while I'm modifying the queue or trying to read the queue. I don't want queue size to be called while I'm enqueuing something, because I might get into a state where I'm interrupted as I'm inserting something, and now my queue is in an invalid state, where I've got the number of nodes in this list is not equal to the actual number of reachable nodes, so I want to lock this. I want to prevent concurrent access to this thing. I'm going to say enqueue the job to the pool's list of jobs. And then I want to send a signal. Hey, there's work to do now. If you're sleeping because you got to that condition variable and there was no work for you to do, wake up. Please wake up, because now there is something for you to do. So I'm going to say pthread cond signal. I've only added one thing, so I only really want to wake up one thread. I could wake them all up and have whoever happens to wake up first get it, but I think it's just more straightforward to start exactly one thread up instead of starting up a bunch of them. So I'm going to send a signal on pool work CV. And then I want to release the lock so that the thread of execution that's waking up from that pthread cond wait is able to get the lock. So I'm going to say pthread mutex unlock pool mutex. All right. Once I've done that, I'm going to change this status variable that I've got up here to be equal to 0. I succeeded in enqueuing this work and asking some thread to start up and begin to do some work here. Is everybody okay with this so far? So we've called thread pool create. We started up end threads. We've launched end threads. End threads have started. And if they have not been told to shut down immediately, they're all sitting here waiting for work to do. They're all stuck. They're all blocked. Nobody holds the lock right now. Eventually, someone is going to call thread pool queue. We're going to acquire that lock. We're going to put a job into the queue of jobs. We'll send the signal for them to wake up, and we will unlock the lock. one thread of execution is going to be able to become unblocked from this cond wait statement. Once it becomes unblocked, it holds the lock, and it's going to be able then to go through the process of dequeuing that job, unlocking the lock, and then doing the work that it's been asked to do. And then eventually it will either go back to sleep, or there will be more work in the queue for it to do. Did you have a question? Okay. The very last thing that I want to do here is I'm going to go down here to thread pool wait. We create the thread pool, we submit work to it, work gets done, and then eventually I want to shut everything down. Finish whatever task you're currently working on and ignore if there's any more stuff in this queue for you to work on, just shut down. If the pool that was passed to us is not null, then what I'm going to say is pool wait is equal to true. You should start shutting down. If you ever get to a point of checking to see if there's work to do, you should shut down because there might be work to do, but this condition is now true and you should start shutting down. While there are still threads left, I would like to lock the lock. I would like to send a signal. If you are sleeping for some reason while we're shutting down, wake up. Notice that the flag has been set and shut yourself down. And then I will unlock the lock. So that when these things are waking up, they are in fact able to get hold of the lock that is passed to them. And then end of loop. So just keep doing this until all the threads have exited. I'm going to zoom out here. I'm going to quit my interface. I'm going to run make. So my make file, just like last time, is in the parent directory. So I'm doing -C. And I miraculously succeeded in typing it all in without any syntax error. So I feel great about that. Yeah, that's really good. Oh, thank you. Yeah. Now that you do that, I wish that we all just had like a little buddy on the corner of our screen that when we run make and it just works, that it would just clap for us. There'd be a nice little sound. And then when it doesn't compile, it would be sad trombone sound. Yeah. I'm going to run this. So I've got this thread madness. It should have finished by now. It should have finished by now. It should have finished by now. Okay, it does finish sometimes. All right, so we got a bug. We got a bug. If you noticed where I put the bug, congratulations, but let's now try and figure out where the bug is. So I'm going to use LLDB to do this. Debugging processes, as I'm sure you are all well aware at this point, is painful. It is painful, partly because tools like LLDB by default do not follow child processes. You can make it follow a child process, but gosh, it's painful to switch back and forth or cause your processes to stop executing in just the right spot so that you can attach LLDB to them to figure out what's going on. Doing this with threads is much nicer. It is much, much nicer. It's still hard because we have to think concurrently about this stuff, but it is much, much nicer, and it's all just built into LLDB. I have launched LLDB with Thread Madness. I'm going to hit R here. I'm going to hit R again. Good. Okay, I want it to get stuck here. So the first time I hit R, there was lots of output, but it basically just said, okay, it finished, and nothing happened. I want to get into the state where I've got this bug. So now everything appears to be stuck right now. When we're in this stuck state, I'm going to hit Control-C on my keyboard. Control-C here is not terminating the process. It's not sending the interrupt, it is sending the interrupt signal, but LLDB then is sending the stop signal to our process. This is not saying shut down, it's just saying stop what you're doing right now, please. I'm going to zoom in on this pane so that we can see better what's happening here, and I'm going to make this just a little bit bigger. The first thing that we can see is that whatever thread was running is stuck on this lock wait. There's lots of other stuff here. The word futex keeps showing up. pthread locks in Linux are implemented using this kernel structure called a futex. On Windows, it's different. On Mac OS, it's different. But on Linux, it's using this structure that's called a futex. And we will speak no more of futexes. All you need to know is that it's a locking structure. We can see that we've got this thing stuck on a lock. But what I want to see is, I'm going to run thread list. Thread list here tells me that there's 9 different threads running, and they are all stuck. They are all stuck on this futex. They are all stuck on lock wait. I'm going to zoom out just a little bit so that we can see everything. Thread number 1 is the one that we were just looking at that is stuck on this lock. What I would like to do is I'm going to switch to a different thread of execution in my debugger. I'm going to do that by saying thread select, and then I'm going to pick number 7 here. So thread select 7 says I'm switching to thread number 7 in this output. I want to go up. So the up command in LLDB says move up 1 stack frame. And then I want to go up, and then I want to go up, and then I want to go up. Okay, here we are. Right now, this thread of execution is stuck on line 40. It's stuck on line 40. It's waiting for this mutex to be released by some other thread of execution. I'm going to print out this mutex. I'm going to say p pool arrow pool mutex. And what this tells me is that the thing that currently has this held is thread with ID 601639. So I'm going to run thread list again. 601639 is here. It's thread number 6. This is the thread that currently holds this lock. So I'm going to do thread select 6. I'm going to go up. 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 This thread currently holds the lock, and it's trying to acquire the lock. I guess pthread mutex lock is not smart enough to know that the thread that's currently executing currently holds the lock that it's trying to acquire, and it's just blocking because that lock is held by somebody, so you cannot also acquire this thread's lock. What we found out is that a thread is able to get into a state of acquiring the lock and then not releasing the lock. And then it tries to acquire it again, but it can't because it already holds that lock. So there's somewhere in our code where we have acquired the lock, but we haven't released it for everyone else to use. So I'm going to hit Control D on my keyboard here to terminate LLDB. We're able to list them, we're able to switch between them, and we're able to move around stack frames with that. Yeah?
Can you repeat up to again?
Sure. So I'll run this one more time. I'll run it again. Okay, I'll hit Control C. The up command, if I type in backtrace here or just B, you can just type in B. This will print out, it's not B, it's BT. If you type in BT, this lists the entire stack frame, the stack for this thread of execution. Up and down will cause us to move between the frames of the stack that we currently have. So right now, if we're inspecting the state of where we are, we're at this stack frame. When I type in up, I move to this stack frame. When I type in up, I move to this stack frame. When I type in up, I move to this stack frame. And when I type in up, I move to this stack frame, which is now in my code, so I can actually see what the variables are that I'm trying to inspect. You can also go down. If you type down in instead of up, it will just move back down the stack to the bottom of the stack that you've got. So I'm going to quit this. I'm going to edit my code one last time here. I got to quit this because I have it open in another terminal here. I'm going to point at the place where we are acquiring a lock and then potentially not releasing it. Here's the order of operations. We create this thread pool. One thread at a time gets started. One thread at a time will be able to enter this critical section. Each one will try to wait on this condition variable, and they will all get stuck, and they will all release the lock. So far, so good. Everyone has released the lock. Nobody currently holds it. Eventually, somebody submits a task with that thread pool queue function. The lock becomes acquired by that thread. It adds something to the queue. It sends the signal, and then it releases the lock. So down here, in thread pool queue, we acquire the lock, we enqueue something, we send the signal, we release the lock. So far, so good. We send the signal, and somebody wakes up here, and then we will immediately call thread pool wait. And we will set the pool wait value to true. I want you to stop running whatever you're running. I don't want you to take any more jobs. I want you to shut down. A thread of execution will get into the state of, I will have the lock acquired. I will go back to the top of my loop. This part here, where we're testing to see if there is no work, may or may not be true, but in that we've just signaled somebody to wake up, this is false. We will get to this point, and we will check to see, is queue size bigger than 0? That is true. We just added something to the queue. And not pool wait, but pool wait is now true. So this expression will become false in its entirety. But I hold the lock. I hold the lock. I hold the lock because when I woke up from pthread wait, I get the lock. I'm only able to start executing code if I'm able to hold the lock. I hold the lock. This is false, so I just go down here. I do not unlock the lock. I do not release the lock. I'm going to add some code here. I'm going to say else if pool wait. If we have been told to shut down, then release the lock. If we've been told to shut down, then release the lock. Our order of operations now changes to, I have been signaled. There is work for me to do. I wake up. I hold the lock. I check to see if this statement, this part of my statement is true. It is no longer true because there is something in the queue. Then I get to my conditional statement and I check to see, is there something in the queue? Yes, there is indeed something in the queue. But my pool wait has been set, and so now my expression becomes false. So I go to my else if, and now I test to see, is this wait set? Is this flag been set? And if it has been set, I still hold the lock, so I am going to release the lock. Once I release the lock, I'm going to go back up to the top of my loop here, and my pool wait has been set to true. So now this expression will also become false, and we will leave the loop, and then we will try to acquire the lock again, decrement this to say that we're shutting down, release the lock, and then return from this function and exit. And then eventually everybody will be able to shut down because they will all be constantly signaled until that number of threads is equal to 0. All right, okay, so I'm going to put some version of this code up on the Git repository after today's class. What I want to just quickly finish up here what the hell are we doing with these resource pools? We've just spent 2 classes talking about thread pools. Me, Franklin, believe that this idea of resource pools is important enough that we spend 2 classes talking about it. Thread pools and resource pools in general are valuable for situations where you've got lots and lots of short-lived tasks or lots and lots of things that take less time than acquiring the resource in the first place. So if the cost to launch a thread, the time required to launch a thread is significantly more than the time to just call the function, having these threads already started up, the cost of creating the threads get amortized across all of the jobs that you're sending to this. With connection pools, with databases and web requests, the cost of making a connection to the database is often more expensive than it is to service the request, the HTTP request, or to service the SQL query that you're running to that database server. So having this thing created and then reused and reused and reused and reused allows you to reduce the overall cost of doing that thing. The other option is what you were describing. So we pick a value that says, I only ever want 10 threads to be running at the same time. I do not want to launch 500,000 threads, all trying to get access to the processor at the same time. I'm just going to launch 10 of them. And 10 will be the most number of threads that will ever be concurrently executing. So we're going to minimize the amount of context switching that we have to do between all of these threads. And we're going to avoid this idea of thrashing, so constantly doing context switching, and that context switching just adds up and adds up and adds up and adds up. We're going to skip this. We'll do this next class. You should, at this point, be able to use condition variables in a program, and I otherwise hope that you have a great day. Thank you for the 2 minutes of your extra time, and I will see you all on Wednesday. Bye, everyone.